Hi, so today we're going to be doing the integral test for convergence. And the integral test for convergence is the third test that we're up to for all the tests we need to do for an infinite series. Just as a side note, the second test was the nth term test. Okay, I just wanted to jot that down for you to make sure that that was clear and we can keep track of all the tests we've been doing. There is about 9. There are more if you want to do them, but there's 9 that are needed in our course. Okay, so the integral test for convergence, okay, says that the implicit rule a sub n is a function. Usually we're used to functions being f of x, so we can change that over into f of x. You're going to see that we're going to do that as like our very first step when we do our examples. And f has to be a continuous positive decreasing function of x. Okay, where x is greater than or equal n, so n is a positive integer. So that means there are 3 conditions, okay, 1, 2, 3, as you're copying down. These 3 conditions must be met. So I should circle that there are 3. I'm going to make those 3 conditions we're going to check to meet as steps 2, 3, and 4. Okay? Well, now that we get through this whole process, what happens when we look at this series, okay, where we're looking at the sum of a sub n as, and this is an important one, the subscript, let me write it so it's like a little bit bigger, is little n equals big N as a sub n, okay, as it goes towards infinity, we have all these values. So we have to make sure that it does make sense that n has to start at this value here, okay, when we have to do the actual tests. It makes more sense when you actually see an example, okay. So let's get to our examples. Hopefully you had some time to copy this down as I was explaining everything. Okay, so the integral here, okay, kind of comes about to actually see if it does converge. So think of that as like a step 6 or step 7, however many steps afterwards that you have to do that integral. Again, we're going to see that in the examples, which I'm trying to get to. Just making sure you're taking the time to copy it. Once again, if you need to pause or stop the video, you can do so. Okay. Okay, so here are 2 examples. Determine whether each series converges or diverges. So in number 1, we have an infinite series, and we should be able to tell what a sub n equals, okay? So we're going to do that as our first step. So number 1, step 1. So we're going to change over a sub n into a function f of x. So instead of 1 over n squared plus 1, we're going to look at 1 over x squared plus 1. This is easier to understand what our function is. Okay, so we're looking at values of x that are going to be greater than or equal to 1. So that's coming from like the value over here of 1. So that comes important later on to make sure that everything kind of checks out. So next thing we need to do is, and it doesn't matter really any order that you do this in, to see if f is continuous, if it's positive, and if it's decreasing. Okay, so we know for values of x, okay, that f is going to be a continuous function. We can plug in any value of x there, and we're going to get an answer. Okay, so we're going to say f of x is continuous for x is greater than or equal 1. Okay, we're doing number 1 here, and we're up to step 2. Step 3, okay? So I did the continuous part. Is it positive? So it is positive for all values of x. If you're not really sure, then you can actually just start plugging in values, okay, into your function and see what actual answers you get for y or f. So f is a positive function. So this leads us to number 4, okay? And 4 is kind of tricky. So how do we know for sure that it is a decreasing function? Okay, well, if you know your common function there, 1 over x squared, it's just, you're affecting that you're just adding 1 to the denominator. So you know that it is decreasing. Your values are going to get smaller and smaller. But you can do something else. You can take the first derivative, okay, and test to see if it is indeed decreasing for values of x that are greater than or equal 1. So there we go, back to that again. So if we were to rewrite f of x, I would do so as x squared plus 1 to negative first power. So we can take the first derivative, and I'm sorry about that. That should be a plus sign. Multiply all of that by 2x. Okay, so we could rewrite this as negative 2x over the quantity of x squared plus 1 squared. Okay, and we have to consider, okay, is this defined for every value of x? Well, we can take the denominator, set it equal to 0 to make sure, yeah, it is. You know, not going to have an issue there. But we can also get a critical number by setting our derivative equal to 0. And finding, well, when x is equal to 0, okay, that would be a critical number. And then you can test before and after that. We're really going to test after that because, once again, x has to be greater than or equal to 1. So what happens if we plug in 1 or anything in the interval from 1 to infinity? We're going to get a negative answer because look at that numerator. Okay, so that means that our function f of x is decreasing on that entire interval. So it's good to know FDT. It's a great kind of review when you have to do these series. So the next thing we're going to do is like make our conclusion, okay? So since it does decrease, the integral test does apply. And then that leads to us using integrals because it is the integral test. So this is where I said, well, hey, maybe like steps 6 and 7. This is where we're going to tell whether it converges or diverges. By the way, if all 3 criteria, and it has to be all 3, are not satisfied, you cannot apply the integral test and you wouldn't be doing the next few things, okay? You may be trying to do a different test to help you out. So let's take a look at our next step here. And that is integrating 1 over n squared plus 1. That's an n, by the way. Okay. From 1 to infinity. So this is an improper integral. And we're going to use an n or we can use an x. If we use an x, then we're using our function, and I can erase that ugly x that I wrote. I mean n. It was not clear. So we're going to make that x. And if you remember improper integrals, I'm going to replace the infinity with b and say we have the limit of b as b approaches infinity of the integral from 1 to b of 1 over x squared plus 1 dx. So this actually happens more than once. This is I've seen this as an example over and over again. in the textbook, workbooks, and online with like practice problems from like the AP tests. If you look at this expression, okay, there's a derivative that has, or I should say an expression that has this as its derivative, and it's the inverse tan. Okay, so you have to practice your improper integrals, but you also have to practice your derivatives and your antiderivatives, so that way we can do these types of problems. Okay. So I'm going to take the limit as the inverse tan of b as b approaches infinity, and subtract the limit of 1, actually the inverse tan of 1, as b approaches infinity. You don't need to write the limit notation. This is going to be an actual answer of pi over 4. Okay. So now let me make this part a little clear, because that was really not clear. That was supposed to be an infinity. Okay, so with that being said, you need to kind of like memorize this, that what its graph looks like, what its boundaries are. Whenever we're working with the inverse trig function, the inverse tan of x, okay, we're restricted to have values of x between negative pi over 2 to pi over 2. So if b approaches infinity, and the highest value we have for the inverse tan of b, in this case, as b approaches infinity, it's going to be pi over 2. Okay? So just kind of remember this. Okay, this is our range. This is what values we're using, okay, with our inverse tan. Well, that means we actually have an answer. We have pi over 4 as an answer. Okay, so our series converges. To what, we don't know, but we do know that it converges. So let's take a look at the next one. Okay, so now we're doing number 2, but we're going to do step 1. So we're going to take a sub n and rewrite it as a function f of x. So we're going to say it's ln of x over x. Okay, so we're looking as x is greater than or equal to 1. Okay, again, it kind of started at 1, just so happens to be for this problem. Next step, so number 2, we're now doing number 2. We want to talk about f of x. It's got to be continuous, it's got to be positive, and we need to make sure it's decreasing. So f of x, would it be continuous for values of x that are greater than or equal to 1? Yes, because we can take the ln of 1, that is 0, okay, and you can have 0 over 1 as an answer. And then we can continue to plug in any value of x that we want, and we would still get an answer. So this is really, really super good. All right, next. So is f of x positive? Okay, that means that if we were to graph this, is it entirely above the x-axis? All right, well, like I said, you can start plugging in values. It can equal 0. That's no problem, okay? It would still be considered a non-negative function. So if I plug in 1, no problem. Even if I plug in 1/2, okay, we are going to be able to get a positive value. So this is good. Again, it's positive for values of x that are greater than or equal to 1. Okay? So now, if it was a calculator question and you throw this into a graphing calculator, you may be like, oh, it's below the x-axis, so we're not going to be able to use this test. Well, that would be incorrect. Okay, so it works out. We can use the integral test for this example. So me saying that, let's go to number 4 and just be careful. You can do this part. I should say number 3 you can do without the graphing calculator. So number 4, to see if f is decreasing, we're going to take f prime of x, that was supposed to be an f. And with this, we would probably do quotient rule because we are dividing by x. So bottom derivative of the top minus top times the derivative of the bottom, which is 1, we don't need that there, over the bottom squared. Okay, so we end up with 1, okay, minus the ln of x over x squared. So now we can have x equals 0, okay, but it's not even in our values here. We want to go from like 1 to infinity. Okay, let me just rewrite this. All right, if we set that numerator equal to 0, then the ln of x would equal 1, and that would be e. Okay, so what's going on? Okay, so we actually have a critical point to kind of test our interval. So if we go from 1 to e, which is about 2.718, and e to infinity, what happens is we end up looking at positive values and then negative values. Okay, so we know that it's decreasing for values of x that are greater than or equal to, we can say, to e, which is within our interval, but we would have to alter that. It should really start at e in order to actually do the integral test from convergence, okay? If you do, though, you're going to find that it diverges anyway, okay? So this one here, f of x, okay, actually I want to say f prime of x is greater than 0 for x is greater than 1 but less than e. Okay, so another test may be more applicable. Okay, but in other words, okay, this is just a side note. The integral test cannot be applied. All right, so like I said, if you do this test, okay, for let's say values of x that are greater than or equal to e, you're going to end up getting infinity as an answer. And if that's the case, let's change that to an e, then you would state that it diverges. So it's just a little heads up, in if it doesn't converge, okay, it doesn't give you an answer that is a numeric answer. If, let's say, it's something with no answer or infinity, you're going to say that it diverges, okay? So that's it. So hopefully you understand the integral test for convergence, and good luck on the practice.